Hey everyone, it's Mr. Canfield. Today we're going to be doing something called proofs, which might be exactly what it sounds like. We're going to prove that something's true. We're going to start somewhere and end somewhere else and say, well, if this is true, then this is true, then this is true, then this is true. That's what we're doing. So it's a pretty short lesson, a pretty heavy idea, and we're going to introduce some new vocabulary in the process. So here we go. Our warm-up is just a it's just an equation, and we're trying to solve it. So let's go and solve this equation. So you should try it on your own, and then see if we do the same thing. So seriously, pause the video, try it, go through it, do it, see what you get. Did you do it yet? How about now? How about now? Okay, so I'm going to do this twice. I'm going to do this two different ways. So the first way that I'm going to do it is the way that I think works for a lot of people, where they see an x's on both sides, and they just say, well, let me get rid of the x on the right-hand side of the equation. So I'm going to subtract 8x from both sides, subtract 8x from both sides. When I do that, on the right-hand side, I'm left with negative 20. On the left-hand side, I'm left with, let's see, 5 minus 8 is negative 3, and then plus 37. So then now it looks like a normal two-step equation, so I'm going to get rid of the 37 first by subtracting the 37 from both sides. So negative 20 minus 37 is negative 57. There's a negative 3x here. And then I'll divide both sides by negative 3. So 57 divided by 3, that's 20, but 1 off, so it's 19. Okay, because 20 is 60. Sorry, just doing some mental math. So I get, and then a negative divided by a negative is a positive, so I got 19. So that's one way to do this problem. Another way to do this problem, and this is my personal way that I would probably do it, is I see the 5x and I see the 8x. I know we subtracted 8x from both sides last time. I wouldn't do that personally, but I'm also comfortable with x being on either side and solving it. So what I like to do is I go, well, which one? I'm going to have to subtract one of these. If I subtract 5x from 8x, I'm left with a positive 3. So I would prefer to do that. And so I'm going to do that, and that's going to cancel the 5x. Well, I'm going to add the 20 at the same time, since I know I'm going to have to do that in a second anyway. And so now I'm doing two steps at once, and I'm left with 3x is equal to 57. And yes, that was not me messing around. I do legitimately write the right side first and the left side. That's how I thought about doing it. And I'll divide both sides by 3 and get 19 again. So there are still other ways to do this equation, to solve it, but there's two ways. The left way is very common and very useful for people who are uncomfortable with these, but the more comfortable you get, something like this saves you some writing and some time. All right, so let's move into our lesson. Believe it or not, what we just did here, this was a proof that x was equal to 19, what we just did. We just gave evidence to show along the way that if this opening statement is true, well then you do this, therefore x has to be 19. That's all a proof is. A proof is laying out evidence, or another word for that is justifying our statements. So let's look and see what William did. So let's blow this up a little bit. Ignore. You're not seeing anything, okay? You see nothing. Okay, so let's say William is given this equation. On the next step, he wrote 84 plus 6x is equal to 108. And he said what he was doing here was using something called the distributive property. And if you're not 100% sure what that means, he took the 6 and distributed it to the 14 and to the 8. He wrote 84 plus 6x is equal to 108. Okay, well, what did he do next? the next statement he gave was that 6x is equal to 108 minus 84. He moved the 84 to the other side using subtraction. Subtraction property of equality. These fancy sounding things, I don't usually use this sort of language in class. The only time in my life I've ever had to use this sort of language was when I was in 9th grade taking geometry, and my teacher made me made me use this sort of language. This is ultra fancy language that is not really important anywhere else. Simplify I think that's okay. You understand the word simplify, hopefully. 108 minus 84 is 24. So how does he finish it? Well, he divides, right? So, he wrote multiplication property of equality. And we could say he's technically right, but you might want to say, well, let's use the division property of equality. And I could be wrong. There might not even be a division property of equality. Don't worry too much about that. If I piqued your interest, division and multiplication are two sides of the same coin, just like subtraction and addition are. Adding the opposite is the same as subtraction. Multiplying by the reciprocal is the same as division. So our Williams justification is valid each step. What might you change? So that's the part that I might change. Can you justify another series of steps that results in the same solution? So like we did earlier, can you do some other steps to wind up at the same solution? There are other ways to do this. I'm not super concerned with you figuring that out right now, but there are. If you divide by 6 at the very beginning instead of distributing, that's a really cool way to do this problem and save you some time. So anyway, this is the idea of a proof, that you go through each line of reasoning and you say what your reasoning is. In algebra, it's annoying. In geometry, it can be really important and necessary. Like in algebra, if you scribble all this out, most people are going to be able to follow what you did here. In geometry, that's not always the case. So let's look at a situation in geometry. Oh, I changed the color. Go back to the, actually that's kind of nice. Okay, I'm going to leave that. So a theorem is a conjecture that is proven. So we're going to talk about something called the vertical angles theorem. So you've probably heard the phrase Pythagorean theorem at some point in your life. If you haven't, don't worry about it. But there's this idea in math called a theorem. And theorem is very similar to this idea of theory. In science, that's just a theory, that's just a theory, a game theory. No, so theory was this idea that I think this is true and there's some evidence to back it up. In math, theorem is, it's stronger than that. Theorem is, this is a true thing, and we proved that it's true. Thing that people proved to be true. That's like, this isn't the math definition of theorem. This is like I want you to understand what the word theorem means. A true thing that's not just like, yeah, okay, that's true. It's like, it's definitely true. It's been proven. It can't possibly be false, kind of thing. So the first theorem that we're going to talk about is called the vertical angles theorem. I actually forgot that this was a theorem before teaching this lesson because I just remembered it to be, I knew this thing was true. So let's talk about what vertical angles are. So what did I do? I took two lines and I intersected them. So vertical angles, let's point out some vertical angles. We can call this guy right here and this guy right here, we call them vertical angles. And you may be like, oh yeah, because they're right on top of each other. Like they're vertical from each other. One's here, one's there. But if this was turned sideways like this, they're still called vertical angles. So don't get confused and think that vertical angles always have to be above and below each other. So similarly, we could say like this angle here and then this one down here, we could call them vertical angles with each other. So now that idea is out of the way, let's go and talk about this theorem. So we've got angle 1, angle 2, and angle 3. So out of these three, what are the vertical angles? Just to make sure you understand the nomenclature. Right, 1 and 2 are vertical angles. 3 would be a vertical angle with 4 if we named that, but we're not even naming it. So given that 1 and 2, angle 1 and angle 2, are vertical angles, that's our given statement. So whenever we're proving a theorem or going through and doing a proof, there always needs to be some amount, something given to us, some situation. And then from that situation, we need to show one squiggle on top of an equals 2. In case I haven't shown that symbol in class before, that is the congruent symbol. So if you look at this, you might think, yeah, 1 and 2 look like they're the same size angle. We need to somehow prove this. So to prove this, I might need to throw a couple more things out just to make sure that we understand. So a proof is a convincing argument that uses deductive reasoning. A two-column proof in which the statements and reasons are aligned in columns is one way to organize and present a proof. Okay, so earlier, this William thing, this statements were over here on the left, reasons were over here on the right. That's really all that we're going to be doing here. We're going to be doing what's called a two-column proof. And yeah, so here we go. Statement. You usually start with the given when we're going through and proving things. So we could say statement. 1 and 2 are vertical angles. My reason for that? Well, they told me it, so it's true. We know that's true. Okay. So what else do we know then if they're vertical angles? Well, the first thing that we know, this is the first part where I'm like, this might be new language, so I want to make sure we know this. So we're gonna come back to this in one moment and go back over here. The other thing we should talk about, if I have a straight line segment and then I pop this guy off here, do you know? I know you can't answer me right now. Do you know what angle 1 and angle 2 add up to if they're on a line like this and there's an angle popping off? If you did not know, they add up to 180 degrees, and they have a special name when they add up to 180 degrees, and that is supplementary. We say supplementary angles because they add up to 180. So anytime you have a straight line with a offshoot, those two angles have to add up to 180. Because if we take all that away, I said if we take all that away, anytime you have a straight line like this, a perfectly straight line, we call that a 180 degree angle. If you throw a dot in the middle. Okay, so we could say that if we look at this, we have angle 1 and angle 3. If you ignore all this down here, you can see that 1 and 3 are on a straight line together. 1 and 3 have to add up to 180 because they're supplementary angles. So our second statement is that the measure of angle 1 plus the measure of angle 3 has to be 180. And I might even say that this is statement 3 down here, but they use it as part of statement 2. And they say, additionally, if you just ignore, this up here, 2 and 3 also have to add up to 180. That's true. So what we could do then is, well, if 1 plus 3 is 180 and 2 plus 3 is 180, these both add up to the same thing. That means that what we could do is we could actually take that and say, well, then those have to equal the same thing. They both equal 180. They equal each other. So using what we call the transitive property of equality, we say 1 plus 3 and 2 plus 3 are equal to each other. This is not necessarily a statement that you're going to have to be able to say to me. This is called a transitive property. So I think that's part of the stuff we skipped in 1.6. But hopefully you see that connection there, that, well, if this equals 180 and that equals 180, we can say that they equal each other. So, so let's keep going. So if they're equal to each other, wait, hold on. This first one says that 1 plus 3 is the same as angle 2 plus 3. I think it goes through too fast. Angle 1 plus angle 3 is the same as angle 2 plus angle 3. Do they use congruent or equal? They're using equal, okay. So if you look carefully, they both have this. You see that? Angle 1 plus angle 3, and then angle 2 plus angle 3. Well, think about that for a minute. What does that mean? It means that angle 1 and angle 2 are the same thing. Because whatever angle 3 is, it's adding the same amount to 1, and it's adding the same amount to 2. That means we started in the same place if we ended up in the same place. So, or you could just say, hey, subtract the measure of 3 from both sides, and boom, boom, you'd be left with an equal statement. So, using the subtraction property of equality, therefore, we could say, see, that's silly. I would stop there. I wouldn't think to say that. That's kind of a silly. This is one reason people hate proofs. Did you know that? People hate proofs. One reason they hate proofs is because there are these extra lines of technicality that nobody cares about. Like, sure, if I'm going to try to write a scientific paper, maybe I need to include this last statement here. But if I'm just trying to convince somebody, by the time we get to 4, we're good. Change lots of colors. Woo! Okay. It's back where I started. So that's the idea of a proof in geometry. So here's what's so powerful about this and why we bother doing this. Do you know angle 1? Do you know angle 2? No. You don't know angle 1, you don't know 2, you don't know 3, and you don't know 4. All you know is that given any random x like this, these two angles are equal to each other. And you could go on and you could even prove that if we brought angle 4 in, 3 and 4 are equal to each other. They might be different than 1 and 2, but they're going to be equal to each other. With this, no matter the situation, I now know, boom, boom, 2 random lines, doesn't matter. I know that that and that are equal to each other. It's proven. It's undeniable because it's been proven. And so anytime I want to say that, I'm like, nah, these have to be equal to each other. Why? Oh, because they're vertical angles, and that's what we've proven that vertical angles do that. This is why we use proofs in math. This is why proofs are really important, and this is why they're good. When we use a proof, we're able to say forever, oh, that has to be true. 1,000 years from now, draw 2 random angles. Boom, boom, done. Oh, they're vertical angles. So they're equal to each other. It's the way it works. So if that does not feel powerful or useful, that's fine. Later on in your life, you might understand why that's important or useful. And you don't need to get it for now. So anyway, here we continue. All right. So here's our next one. It says, the measure of angle 1 is equal to the measure of angle 2. I'm going to put a little marking on there to remind myself. And the measure of angle 1 is equal to 105. So I'm going to write it on here on 2. 105. Prove the measure of angle 3 is 75. Oh, that's not that complicated, is it? You might go, well, what do you mean prove that angle 3 is 75? It's telling us the answer. it's another way of saying this. Hey, what's the measure of angle 3? Oh, how can I find that? Well, let me see. Oh, you know what? I did some work here, and if I want to use a technical proof, so I'm doing this without looking down here. I'm trying to, if I act like I was a student and didn't have access to the answers already. So I knew 1 was 105, and then since we said they're the same, then I know 2 is 105. So that's my first little jump that I took. So let's go in and look at the proof. So our first statement is that 1 and 2 are equal to each other. Sure, that's a given. Our second given is that 1 is 105. Now here's our first logical leap. Our first logical leap is that, well, then we know that 2 is 105 because that was given to us. And if you're like, well, they didn't tell us that at the beginning, but it was so obvious. It's okay that it was obvious. They didn't tell us. We figured it out. Next part, if I want to find out what angle 3 is, well, I know that 2 plus 3 together, that's one of those straight 180-degree angles. It's called a straight angle. Sorry, I didn't use that phrase earlier. It's called a straight angle, so they have to add up to 180. So I know that 2 plus 3. Okay, that's one way to call it. That, sure, or straight angle. You could say, there's so many different, I would just start here. I would say angle 2 plus angle 3 has to add up 180 because, all right, cool. We never learned that theorem. But, okay, so somebody else went along and proved it was 180 degrees. Great, thanks. Hopefully you're still with me, that those have to add up to 180. So if I just figure that out then, 105 plus something gives me 180, and then solve it. So we could just take 180 minus angle 2, or 180 minus 105. Oh, substitute, sure. It's a little silly. So I think that our text is doing us a little bit of a disservice here because it's a lot of extra writing. Let me do my own 2-column proof of this. Or better yet, instead of doing a 2-column proof, let's just do what I would call a paragraph proof. So I would say since measure angle 1 equals measure angle 2, and measure angle 1 is equal to 105, then measure angle 2 equals 105. And then since angle 2 and angle 3, all right, I'm going to use the language they used. Why don't I type? Are a linear pair. They add up to 180. So you could say, since they're a linear pair, or maybe even say, since they are supplementary angles. I would absolutely accept that phrase. Supplementary angles, they add up to 180. Therefore, (105) plus the measure of angle. Oh, I wonder how I get the actual like little angle symbol to show up. I'll have to learn my alt code for that. The measure of angle 3 equals 180. And then you don't need to use fancy language for this. If you just show me how to solve it, you show me the steps. So So the measure of angle 3 then is equal to 75. And if you want, there is a fun thing that we put at the end of a proof. There's a couple of things you can put. One of the things you can put is if you've proven, like you got into the answer, we're showing measure of angle 3 is equal to 75. One thing you can write is QED. This is the fancy thing to write. And then the other fun thing that you can write is you can put a box. But that's the way we say, I'm done. Both of them are the way that we say, I'm done, and I want to make sure I get this right. So I'm going to, QED stands for, it's quad erat demonstratum. I just wanted you to see the quad erat demonstratum. It just literally means, quad means what, and then erat demonstratum, what was to be demonstrated. Which was to be demonstrated, QED. Let me explain that in English. Is QED pretentious? It's pretentious to use it when you're not discussing a proof, and embarrassing to use it if you're just ranting and not even. You're definitely going to sound like you think you know that you're hot stuff if you use the QED, but it's fun. And we're in a math class, so I'm allowed to use it. QED. So why the heck do we write that? So it said at the beginning, we're like, given this, show me this. And I'm like, okay, well, all this is true, right? Blah, 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 blah. So measure angle 3 is 75. That's what you wanted me to show you. That's what QED means. I got measure angle 3 is 75, which was what I was trying to show. Literally, it says, prove this, proved it. That's what you wanted me to show. QED. QED means that's what you wanted me to show, but in fancy Latin. If you don't know what Latin is, it's an old dead language. Okay, I think we got a couple more examples. So we're in a paragraph proof of the congruent supplements. Okay, let's see what that means. Oh, congruent supplements theorem. So, that's the other thing. If you're the person that is the first person to do a theorem, you get to name the theorem whatever you want. So whoever made this theorem named it congruent supplements theorem. Given that 1 and 2 are supplementary and 2 and 3 are supplementary, prove that angles 1 and 3 are congruent to each other. So let's look at the paragraph and see how they do it. So proof. By the definition of supplementary angles, measure 1 plus measure 2 is equal to 180. And measure 2 plus measure 3 is equal to 180. Since both sums equal 180, you can set them equal to each other. Subtract 2 from each side of this equation. So this is where I deviate a little bit. Yes, this is technically like using a paragraph proof. I think this is unnecessary. It's kind of silly. And I think our text does us a little bit of a disservice here, because I think you could just subtract, like just show the work, subtract 2 from both sides. And then say, see, 1 is equal to 3, QED. Whenever we do proofs, I'm going to be using QED just because it's fun. It's a little pretentious, but we get to do it. It's fun. All right. We're at a paragraph proof of the congruent complements theorem. Ooh, we've got a new phrase, complementary. So, supplementary. Remind yourself what supplementary was. Supplementary means they add up to 180. Complementary angles add up to 90. So very easy to mix these up. So let's see, complementary, okay, complementary angles, they add up to 90. So complementary adds up to 90, supplementary adds up to 180. Important, I know I've been saying a lot of these words are not important. These are two phrases that are important for us to know. So make sure that you somehow come up with a mental difference between supplementary and complementary. I always think about it as supplement is like, when you're supplementing something, you're going over and above, like you're putting something on top of. And complementary is like, oh, that's nice. So it's like, it's kind of, I don't know, it feels smaller to me. That's one way that you can try to help yourself remember it. Another way you can help yourself remember it is complement and supplement. If I look at them in alphabetical order, C comes before S, and 90 comes before 180, like in number order, in numerical order. So that's another way to think about it. So anyway, if I want to prove this, let's see, 1 and 2 are complementary, 2 and 3 are complementary, prove that 1 is equal to 3. So if I was going to do this, I'd be like, well, by the definition of complementary angles, we know 1 plus 2 is equal to 90. I'll put the symbols in a minute. And 2 plus 3 is equal to 90. And then using, so there's a couple different properties we could use here. They've been talking about the transitive property, so I'll just use that. By the transitive property, 1 plus 2 is equal to 2 plus 3. All right, so for me, doing a paragraph proof, oh, by the way, this is the only course ever that we do paragraph proofs like this and proofs in general. You don't do this in Algebra 2, you don't do it in Pre-Calc, and you don't do it in Calc, and you don't do it in Calc 2, you don't do it in Calc 3. The only class that does stuff like this is geometry. This is why I'm allowed to change, like, you might be like, but what if in a later course they need me to write it a specific way? They won't. This is the only course where we do this. So I'm going to subtract whatever 2 is from both sides. Cancel, cancel. Then I know that 1 is equal to 3. And I can put the little whoop. And then I'm going to write Q, E, D. I did what you wanted me to did. We did what we were supposed to. Done. So the key thing is that we're including all of the important ideas. That's what proofs are about. All right, last one. This one's a little tricky. And they're going to have us write a 2-column proof. That's fine. So let's see. The measure of angle 4 is equal to 35. So I'm going to start out and just go, all right, well, I know this. So this is my first statement. And this is also, right, I'm just writing the givens. That's how we start, that's how we start 2-column proofs. So you can say given, and say given, and we want to end by saying the measure angle 3 is equal to 70. So we already know the answer. Let's see. So 1 is equal to 2 plus 4. Okay. Oh, well, then the first thing I could say is that 1 is equal to 2 plus 35, right? That's because 4 says 35. So we'd say the measure of angle 1 is equal to the measure of angle 2 plus 35. Okay. Doesn't necessarily help me yet. Ooh. You know what? I see something. All right, so, oh, sorry, substitution. You know what I see? Do you see it? Did you see that? That angle 2 and angle 4 are the same because they're vertical angles. So then, oh wait, this was 3. This would be 4, wouldn't it? Sorry about that. So then on step 5, I could say, well, then I know that the measure of angle 1 is actually equal to 35 plus 35, which is 70 through substitution. I don't grade for spelling, don't worry. And then I'm like, QED, quadera demonstratum. So this is my version of my proof for this. I think it's a convincing proof. I think I've given enough information. I think my handwriting looks like a child's. I am using my mouse. I want to show you another teacher's version of the proof. So, oh, this is a different proof. That's why. I was, all right, okay. So, excuse me. So, here's another proof. I'm looking at what time it is and seeing that this video is going on for 35 minutes. I think I'm going to stop here. It's a, they have their reasons, they have their different ideas. We're not going to do a ton of proofs this year, but whenever we do them, I'm going to do my best to walk you through them and to help you with them, and hopefully see some cool things as we go. All right. Well, I hope this was helpful. Bye.